So good afternoon, everyone. Thank you for being here. Myself, Job Thomas. I'm a PhD student from Osaka Metropolitan University. Thank you for giving me this opportunity for FOSS4G Asia 2026. So let's start with the presentation. So what I'll be showing you that I did for my study is evaluating shoreline prediction models using optical satellite imagery and open source tools. So as we know, coastal regions are very dynamic in nature. These are shaped by natural forces like waves, tides, tsunamis, and storms. Because of these forces, shoreline change rapidly. And it's very important to understand these changes. With sea level rise accelerating and climate change also accelerating, it is very important to understand these changes like erosion and accretion to effectively manage the coastal areas for disaster preparedness and long-term planning, and this can be done by mapping these zones. So the research problem and objective is when a shoreline is derived from satellite, there are some bias inside them. So these bias are tide, because of high tide, low tide, waves which are pushed and pulled at the time of capture, and when the satellite is captured, these shifts are not captured by the satellite. So when these shorelines are extracted, they will be having some uncorrected data errors. So if we don't correct this error, so what we'll be seeing when we calculate the erosion is only the water level fluctuation, not the real landform change. So this study focuses on extracting the shoreline using satellite image and performing tidal correction, and then predicting future shoreline positions using these extracted shorelines after doing the tidal correction. And after that, assessing the accuracy and reliability of the tidal corrected shorelines and the prediction using spatial error metrics. And last, evaluating the shoreline changes for a study area in Japan for Wajima and Nafune before and after the earthquake, which happened in January 1st, 2024. So I'm using two study areas. So first one is San Jose, which is in USA. So the purpose of this study area is to validate the tidal correction. And the second one is Japan, which is Wajima and Nafune, to validate the predicted shoreline for before and after the earthquake. So now data used for both of the study area are, so for San Jose for tidal correction, I've used only one shoreline, which is for 2018, and then I've validated them for tidal correction. And for Japan, I've used almost 27 years of shoreline from 1987 to 2014. And then I've predicted using these shoreline for 2023 and 2024. And then I've done the validation. So the satellite used for these were Landsat 5 to 8, Sentinel-2. And I've also used them and tide data to perform the tidal correction. Tide data have resolution from 1 hour to 1 hour 15 minutes of temporal resolution. And this is the methodology. So in methodology, there are two parts. Part one is to extract the shoreline and perform the tidal correction. So where it uses satellite images, then pre-processing is done, and then shoreline extraction is performed. And then tidal correction is done using tide level, beat slope, shoreline elevation, and then validation is done. So this is done using an open source toolkit in Python. So it's called as CoastSat. And the second part of the methodology is for predicting the shoreline. And this was done by using a tool called Ambur, which analyzes moving boundary using R. So for this, there are two inputs. The first one is shoreline and baseline. So using shoreline and baseline, the transects are created. So transects are just a perpendicular line with respect to baseline. And where the baseline and shorelines intersect, at those points, shoreline positions are captured. Now, in my case, I've used 5 different transect spacing from 1 meter to 100 meter. And once the shoreline positions are captured, the distance are calculated from those points to the different shorelines. And using those distances, shoreline change rate is calculated. Now here there are 3 statistical methods. So first one is endpoint rate, linear regression rate, and the third one is weighted linear regression rate. And using these shoreline changes, future shoreline extrapolation is done, and then validation. Now, this is the tidal correction validation for San Jose. Now, I've used two shorelines. So the red one is the coast-side shoreline where I've done tidal correction. And the green one is the in situ shoreline, which was extracted from LIDAR DEM of 1 meter. And these were tidally corrected. And these I downloaded it from NOAA. And this was the shoreline that I've used for validating. Now, if you see at A, B, C, it shows how close those shorelines are or how far they are to each other. Now, I've compared this using 3 different matrices. So first is the distribution of distance between the tidally corrected and non-tidally corrected shoreline. And this shows around the mean distance of 9 meters. And the second one is the beat slope differences, which shows the mean distance of 0.13 degrees. And the third one is the elevation difference between both of these shoreline, which is almost around minus 0.64 meters. So by seeing at this shows that the tidal correction which was performed is with a good resolution. And now this is the result for shoreline prediction for 2023. Now from 3 statistical methods, so linear regression rate gave the minimum error, and from them, as I mentioned, there were 5 different distance intervals. So 1 meter gave the very low minimum mean distance error. Now if you look at this legend, so it shows the distance error between 2023 observed and 2023 predicted. Now from these 5 classes, 0 to 6.9 meters covers 62% of the area. So this shows that the prediction performed is almost good. Now this is the scatter plot. On x-axis, it shows the predicted distance from baseline, and y-axis, it shows the observed distance from baseline, and this is the reference line. So where the d observed is equal to d predicted, so if the points are closer to this reference point, then it shows that the prediction is good. And here it's giving the R square of 0.904. Now, if you see, there are 4 zones, zone 1 to zone 4. So we are focusing on zone 1, which is Wajima, and zone 3 is Nafune. So as you can see, some of the points are coming out. So if you see here at A, so this is Wajima. So these are the points which are outside. So it shows from 95 to 147 meters is the error. Now this is for 2024 prediction. Now from 3 statistical method, weighted linear regression provided very low, and that's 53.6 meters. This is actually not a good prediction. So in distance error from 2024 observed to 2024 predicted, as we can see, 0 to 27 meter covers the 35% of the area, which is not so good. And the rest from 27 to 230 meters shows the how far the prediction, how off the prediction is from the observed. Now from the scatter plot also we can see it's around R square is around 0.56. So most of the zones points are outlying. Only zone 2 is a little bit closer, and some parts of zone 1, which is Wajima. Now the error that this has provided, in the next further slide I'll show you how it is relevant. So what I've done a comparative analysis of pre and post earthquake. So what I did using the first method, first part of the methodology of extraction of shoreline, I've extracted shoreline for 2023 and 2024 before and after the earthquake. Then I've calculated the distance, and then I've compared the result with the Geospatial Information Authority of Japan. So now what they have resulted is, the result that they have reported is, they have used SAR intensity images before and after the earthquake, and they have seen how much land has emerged after the earthquake. So this red area, it shows the land has emerged, and it's around 200 meters of shift is there. So now, in my case, I've used only shorelines, and using shoreline, the result almost matches with the SAR images which they have done, and this, it almost shows the same result. So this is for Wajima, and this is for Nafune. Nafune also, it matches exactly with those areas. Now the error which we have got in this is almost identical to the same error that we are getting here, from up till 243 meters, and here is also around 230 meters. Okay. So the conclusion, the workflow which was developed, it includes shorelines extraction and tidal correction. It gives shoreline prediction good for before the earthquake, but after the earthquake, it doesn't provide very good resolution. But the error that it gives, it can be used to understand how the shoreline has shifted after the earthquake. And this study shows how reliable the shoreline extraction, tidal correction, and prediction can be used to support the coastal management. And last, it is, as I mentioned in the first point, shoreline prediction after the earthquake was not so good, but the error matches with the land displacement caused by the Noto Peninsula earthquake. So now the future work for me is to use SAR image to extract the shoreline and using SAR to generate bathymetry. Thank you.
Okay, we have some time for question from the audience. Any question? The audience? Okay, Job, so I have one question. This time the study area is from which side of the ocean from Japan?
It's the northwest side.
Okay, but normally in Japan you have the Pacific Ocean and the...
Yeah, so the Pacific side.
Okay, so but this time we do only on Pacific side.
Yeah.
Right? Do you think like if we do in another side of the ocean, the result may be the same or?
Yeah, result might be different for the prediction. Yeah, it actually depends on the environment of the shoreline. Is it sandy beach or rocky beach? If it's a rocky beach, there will be no much shoreline change. Wherever there is sand, that's the only area where too much shoreline shift will be there. So that's one of the major factor. And yes, I'm also focusing on to doing at different parts of Japan also. Simultaneously, I'm also trying to use this to a different country or different region to see how prediction changes depending on the region and depending on the ocean.
Okay.
One question from my side.
Yes, sir.
Say, this prediction is related with the earthquake activity. Means earthquake is one of the input for this particular...
No, earthquake is not the input. The input is only the shoreline which was captured during the earthquake and shoreline which was captured before the earthquake.
Okay.
And I've just compared how much is the shoreline shift before and after the earthquake for those two periods.
No, but once we are talking about a prediction model,
yeah,
means we are trying to predict that if event occurs, then what kind of changes will take place. Is it so?
Yeah, but in this model, there is no influence of earthquake. So that's why when the model was used to predict the future shoreline after the earthquake, that's why there was a lot of error.
Because earthquake is such an phenomena where other things like location, intensity,
yes, but
those things will,
Yeah, but it's very difficult to predict earthquake.
Yes.
And so there won't be any model which will predict earthquake when it will be there. So that's the reason the model that I've used is not having any parameters.
No, but the relationship of the existing earthquake with the shifting of the shoreline.
That can be studied.
Yeah, that can be studied and can give a good input to this.
Yes, how shoreline changes after the earthquake and before the earthquake.
Because most of the is more or less same.
Yes.
The earthquake repeatedly occur in the same places adjacent to faults and other areas. So if you tell that these are the earthquakes of these and these intensities are occurring, I think in Japan we must be having a quite detailed seismic zoning maps. So if we have a relationship, establish a relationship with that, then I think we can very well predict that if in future earthquake of this particular intensity occurs at that particular place, then what kind of changes may occur in those areas.
Yeah,
and
true.
then it can be further verified.
Exactly, yeah, that
God forbids, if earthquake occurs, then we can just verify it.
Yeah, that can be done.
Yeah, please have this mic.
So you said you are going to use SAR data.
Yeah.
So there are different bands.
Yeah.
And this area is where the water comes and goes and the influence of water will be more. Which band do you prefer to analyze this particular data?
So the thing is, I'm just doing some literature review for which band to use, but I've come across a satellite called SWOT. SWOT.
Okay.
So I'm just trying to go into deep what all the features that it provides, how to capture the data and how to pre-process it.
Okay.
So it's just in the initial phase.
Because when you say that it has been emerged, the level of distance also varies when you use the band.
Yes, the vertical and the horizontal.
Yes, so you have to be very cautious when using SAR data. That's why I asked. Thank you, sir.
Yeah, thank you.
Job, basically, in terms of the shoreline prediction, before and after the earthquakes, that's okay. You have not taken inputs from the earthquake, but in terms of the model that you used to do the prediction, what is the model you used, and do you have any specific contributions from yourself in terms of defining either a new model or adding to the existing model?
So I've not considered of doing that part because I'm just mainly focusing on extracting the shoreline and how to detect the changes for the shoreline change. So in my study, I just wanted to see how is there any correlation between earthquake before and after the earthquake and shoreline change. So that's one of the reason I just I was just testing it out, how it works, but I have not considered doing that part.
So in case of a non-seismic zone where no earthquakes have occurred or will occur, a stable zone, what would be the accuracy of your prediction?
So for 2023, I've done it for 2023. So here, the accuracy is almost around 0.904.
So in terms of prediction, say for example 2030, how accurate would be your prediction?
Yeah. So for 2030, to validate it, so we won't be having the shoreline for 2030 to do it. So that's why I've done it for 2023 to do the validation. Yeah, validation won't be applicable.
No, Niels Bohr said that prediction is very difficult, especially about the future.
Yeah.
I am from a firm based out of Pune, and we are surveyed the coastline of Mumbai using LiDAR. A lot of much kilometer is surveyed by us. So just to put it out to you, if you want to use the data, taking permission, the government, we can talk.
Oh yeah, that would be very helpful. Yeah. Thank you.
Yeah. Anyone?
Any more question for him? Okay, if not, okay, thank you very much, Job.